So now let's talk about the stress development by the torsional loading. So here one example is given in the left top corner of my lecture note here. So here let me redraw the figure here. So say a circular section is subjected to some kind of torsional moment, okay? Internal torsional moment. Then because of force equilibrium, whether we cut here, 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 so if you cut here, then because of this internal torsional moment on this surface, we must have, this kind of development of shear stress distribution on the surface. So if you consider this cross section, also same, isn't it, right? Also same. So exactly same. So the geometrical condition is the same, and then the stress distribution is the same. This condition is called homologous. Homologous. Okay. Homologous state. So in this homologous state, which means we have exactly the same distribution and exactly the same characteristics wherever we choose the cross section to check the stress distribution. So let's check a small segment here. So if you consider this small segment, so let me exaggerate this small segment. So if you do that, let's consider a small segment on the surface. Then this is homologous situation. Then if we have certain stress field, okay, certain shear stress like this, tau, okay, then we must have exactly the same shear stress in the opposite direction in the left hand side because of characteristics of a homologous situation. And then because of the angular momentum conservation, we need to have the exactly same shear stress in the opposite direction, in the horizontal direction, tau. And then the shear stress, the force equilibrium by the shear stress should be satisfied too in the horizontal direction. There must be shear stress in this direction too, okay? This is the condition, the stress condition caused by torsional moment in circular section here. So if you redraw this configuration in two-dimensional space, it look like this, okay? So this is called, there's no normal stresses in this observation frame. What I mean, in this observation frame, there is no normal stress components. That's why we call this stress state pure shear stress state, okay? Pure shear stress state or pure shear stress condition, the same meaning, okay? Okay, so now let's try to observe this pure shear stress in different observation frame, okay, as we did before. What we want to do is we want to say we have look. So let me summarize again. So we want to discuss the stress field of this member subjected to the torsional moment, and then when we check a small material point, that we found that if you project the stress state into a two-dimensional space, okay, then we have certain the shear stress distributions. Okay, this shear stress distribution is for this observation frame. So I'd like to read the same stress field in another observation frame. For example, I'd like to read the shear stress in this frame, okay? That's what I want to do. This is x theta, for example, and this is y theta. That's what I want to do. basically make sure that the stress state of these two is exactly same, okay? We are talking about exactly same stress state, okay? But because of the change in the observation frame, the stress component must be different. So what we want to do is we'd like to calculate the stress component, okay, using the force equilibrium condition. Okay, let's consider a small part of this section here. Small part of section here. Let's say this angle is theta, and then if you read this normal, its inclination is theta with respect to reference x-axis. What I mean is the inclination is theta here. Okay? So you may think this edge, the blue edge here, it is here. You may think it this way, okay? Okay, so let's check the force equilibrium. Force equilibrium for this segment. The small piece. Let's check it. So I have a segment, okay, I have segment, angle theta, and then subject to the shear stress, okay. And then because we want to read the stress component on this surface, okay, on this surface. So according to our definition of the Cartesian coordinate, there must be two different stress components. One is a normal stress component, sigma theta, and then the other one is what? Shear stress component on this surface, tau theta. Okay? So let's check the force equilibrium. So force equilibrium is always same. The sum of all the forces in the horizontal direction is equal to 0. The sum of all the forces in the vertical direction is also equal to 0. So now let's use the first equation. So what is the first component of the horizontal direction? First one is this. This is the first one. This is the first one, isn't it, right? But make sure that this is force per area, isn't it? That this is not a force yet, so we need to change it to force. And to do so, we need to have the information of area. Then let's say the thickness of segment is given by the t. Make sure that it is cancelled anyway. And then we need this length. How do you calculate this length? This length is, if the height is, say, length L, this length is what? How do you measure this? This length can be measured by L tangent theta, isn't it, right? L tangent theta. So minus, because this direction is left-hand direction, minus tau, and then we need to multiply the length, the thickness, and then length is tangent theta. And the second term, so normal term here, this angle theta, and then plus sigma theta, and then again it's the same. We need to multiply the thickness because this is traction, the force per area, and then we need to consider its length. And how do you calculate its length? This length cosine theta is equal to the length L, which means L 1 over cosine theta. Okay? And then we need to consider this guy, minus tau theta. Is it really straightforward? By the way, this is the normal, I calculate just force, and then we multiply, we need to consider only the horizontal component, cosine theta, cancel. Okay. And then let's check this guy. tau theta t, and the length divided by cosine theta, and then we need to consider the sine component, sine theta. This is equal to 0. And then we do the same for the force equilibrium in the vertical direction. So if you do this, then we can calculate the expression of normal stress in terms of the inclination angle, and then tau, apply the reference shear stress component here, and then the shear stress component on this surface too. So we can calculate in this way. So by the way, the reason that we have sine 2 theta and cosine 2 theta is that we used the half angle theorem of trigonometric functions. That's why. Do you have any questions? So then we can plot the change of normal stress and shear stress depending on different observation directions. Then because this is trigonometric functions, so we can see these periodic changes of the normal stress and shear stress. So here we can find a very interesting point. At angle is equal, observation angle is equal to 0. What I mean, the reference frame, okay, reference frame. Then there is no normal stress component here, as you see, and then we have maximum shear stress component. But if you increase the observation angle to, for example, 45 degrees, then we have very interesting feature here. The normal stress is increased to the maximum here that corresponds to this point, and then shear stress becomes 0. There's no shear stress. Tau theta is equal to 45 degrees is equal to 0. Well, let's consider further. So if you change the angle to minus 45 degrees, the minus 45 degrees, that corresponds here, okay, that corresponds here. Again, the shear stress becomes 0, and then normal stress becomes a minimum, minus tau value, okay. So if you observe this pure shear stress condition in 45 degrees angle difference, then there's no shear stress components, okay. Instead, we have only the normal stress components. So one pair is tension and then the other is in compression. This is very interesting, isn't it? So which means, let's imagine that we have a chalk. So maybe I think you did trick before, right? So if you apply the twisting moment to a chalk, 분필이죠, 분필. Then because here, you know, because of this, we have this shear stress development. Shear stress development. But in 45 degrees, then what happened? So we have here in compression, and then we have tension in this direction. So if a material is brittle, what I mean, you know, the tensile strength is much for like a concrete or chalk. The tensile strength is much smaller than compressive strength. The material would fail by tension first, isn't it, right? That's why the failure surface would form like this, in this direction, rather than, you know, in the tensile direction. So that's why we have helical crack development in the 45 degrees, okay? So look at this. As you see, we can find a very nice helical crack development here. Clear? Okay, here I'd like to take another 10 minutes break.